Hello, my name is Dane Jacobson, a senior at the University of Wisconsin-Madison studying computer science and math. Today, I'll be going over my work in researching physically informed neural networks applications and modeling the Cahn-Hilliard equation. The purpose of this presentation is to give background, problem overview, and results, along with the code used. Let's get started and first understand what exactly a pin is. First and foremost, this presentation assumes some basic knowledge of neural networks. With that out of the way, let's dive into some background. Pins, or physics-informed neural networks, encode physical laws into a neural network by enforcing partial differential equations as constraints. Hence the physics-informed aspect of the acronym. As in typical neural networks, automatic differentiation is used to guide backpropagation. But this time, we use initial condition, boundary conditions, and PDE residuals to guide training. Please note that accurate and convergent solutions are predicated on residuals being accurate themselves. By embedding physical constraints within the neural network architecture, pins are able to generalize better and require less training data compared to data-driven approaches. Note that data for physics-based problems are quite hard to come by, and this is a large reason why pins are studied. It's why they are more efficient than data-driven approaches. Now, on the figure to the right, we see a basic pin architecture, with the traditional neural network being governed by the physically contexted loss function. Now, let's get a better understanding of the Cahn-Hilliard equation. The Cahn-Hilliard equation is a fundamental model in materials science. We'll study it in two dimensions where it governs phase separation in binary mixtures. Now, the way that I like to think about this is oil and water. These liquids do not mix together, but if they're in a jar, when you shake them up, how do they disperse over time? How do they separate over time? This is what the Cahn-Hilliard equation governs. Intrinsically, the Cahn-Hilliard equation is a fourth-order nonlinear partial differential equation. This will cause problems down the line, but for now, let's just focus on the equation itself. In the equation, the variable h represents the concentration field. This can be represented by a visualization at some time. For example, we have in the figure to the bottom right a time of t equals to 0 giving the state of the system at said time. Next, kappa is a mobility parameter describing how quickly our concentration field evolves over time. Now, epsilon is the surface tension coefficient. Visually, epsilon controls the smoothness of the solution, penalizing sharp gradients between phases. Programmatically, this is the PDE that's in our loss function. Next, boundary conditions define how the system behaves at the edge of the domain. In our case, we use periodic symmetric boundary conditions. Note that our spatial domain is on -1 to 1. The initial condition specifies the state of the system at time 0. You can see our initial condition visualized. We use a hyperbolic tangent profile, as seen in the figure. This is where our network starts its computations at. Now that we have a basic understanding of the Cahn-Hilliard equation, we will go into detail on the specifics of our problem. The first problem that we aim to tackle we'll refer to as the forward case problem. What we do in the forward case is we aim to compute the evolution of the concentration field H over time. We do this by approximating the solution over a spatiotemporal domain while satisfying the governing PDE. Just like we've seen in the pin background, our loss function guides our solution in accordance with the initial condition, boundary conditions, and PDE residuals. This isn't that much different than a normal neural network. We keep the aforementioned epsilon a constant value of 0.05, and similarly with kappa constant at 1. You can see to the right the reference results via the White and Zhao paper in 2020, while our results are below. Our results show the evolution of the concentration field H over time. Now we'll go in depth in the inverse case. Do note that the input to the inverse pin is the very solution that we have here in the forward case, our results. In the inverse pin case, we aim to solve the following. Given a time-dependent solution data, can we estimate various key parameters that govern important phenomenon in different systems? Now this time-dependent solution data was the very data that we outputted in the forward case. The input of the inverse pin is x y, and time, representing the concentration field h at some time t. Again, recall that this comes from the output of the forward solution. We aim to infer the unknown parameter epsilon, which is embedded in the time-evolved input data. We specifically set this true value to 0.05. We also use a composite loss function aggregating the PDE, initial condition, and boundary condition losses. Our model predicts epsilon of 0.051. We're able to reach a roughly convergent solution after 60,000 training iterations. As you can see, we get very, very close to the true value of epsilon. Finally, we'll go into detail on some specific training strategies we've employed to enhance the training of our model, first of which being PDE decomposition. Earlier, we stated that the Cahn-Hilliard equation was a fourth-order PDE. The higher order makes differentiation during backpropagation increasingly difficult. To remedy this issue, we introduce an auxiliary variable, mu, to decouple the fourth-order PDE into two second-order PDEs, thus reducing the complexity during differentiation. This results in a more stable training stage, along with reducing computational cost and similarly time spent training our pin. The equation to the right shows specifically how we decouple the Cahn-Hilliard equation. We will see this spelled out programmatically in the code review section. The next strategy we'll go into detail in is adaptive sampling. When training our pin, there were oftentimes subsets of our domain that had high error given our current training setup. One common solution to this problem is error-based point selection. When training our pin, we generate uniformly sampled points across our domain, but there are small subsets that have a relatively high error. We instead locate these high error regions and sample a greater number of points in these specific regions and a lesser on the areas the pin is able to predict easily. The benefit brought forth from adaptive sampling is a more focused learning on regions that need refinement. This enhances solution quality, ensuring that the hard-to-predict areas get enough training points sampled. In the accompanying figure, we could see a visualization of the sampling process, identifying the high error regions and delegating more points to said region. Do note that we only do adaptive sampling in the forward pin and not the inverse. This is because in the forward pin, the output is x, y, and t, and of course that's not so in the inverse. Finally, the last strategy we use is domain decomposition. When training across the entire time domain, we oftentimes see a slower converging and less accurate pin. This behavior is specifically indicative of a complex problem. In our case, the complexity is quite high with the Cahn-Hilliard equation. To help our model more accurately capture the solution at specific times, we divide our time domain into smaller subdomains and enforce interface consistency. A basic decomposition is shown to the right, and this can be scaled to virtually any domain or number of slices. Once the model has completed training one domain, the next is able to pick up right where it left off. We can see an example time domain decomposition, of course, showing how we break up our domain into separate subdomains, with the model performing full training on each. Doing this enables us to have a more accurate solution across the entire time domain. This provides a more scalable solution and improves numeric stability in these complex problems. Overall, these strategies have made the training process faster, more stable, and results in a more robust solution. Now that we have a strong understanding of the problem, methods, and results that we've got, we'll dive into the code that we use specifically in the inverse case Cahn-Hilliard equation. Now that we have a strong understanding of the problem, methods, and results that we've got, we'll dive into the code that we use specifically in the inverse case Cahn-Hilliard equation. In developing and running our code, we use both Google Colab and Kaggle interchangeably, as they offer on-demand GPU usage which speeds up our computation greatly. The cloud notebooks also allow for easily reproducible code that can be ran on almost any machine with an internet connection. Let's start now going over the code and implementation. First, we'll install and import the needed libraries, mainly being the deepxde library. which includes a suite of tools to help abstract some of the more tedious steps of a pin training workflow. DeepXDE also wraps around a traditional machine learning library, and it uses it under the hood for computation. We'll choose ours to be TensorFlow. Next, we define some helpful constants that we'll refer to throughout our code. We have a number of training iterations for our optimizers, loss weights, and their time, x, and y domains laid out. These will be referred to throughout the notebook, so keep them in mind. We use these constants to create a spatiotemporal domain, and we generate points, namely x vals and y vals, to allow us to visualize on our domain. Next, we define our initial condition function. We also have boundary checks that fit our spatial temporal domain. These two boundary check functions will help create our periodic boundary condition in the x and y directions, as seen below. Notice that we also pass our spatial domain via the geom time parameter. Altogether, these functions will be given to DeepXDE to help build out the loss function that governs the training of our pin. Now we'll take a look at our PDE function. This is arguably the most important part of the pin, as it defines the Cahn-Hilliard equation, and obviously this is kind of the crux of our problem. First, we define epsilon, which is a trainable variable in the neural network. If you remember in the inverse problem, epsilon is what we're trying to predict. So we'll set it to a default value of 5. It can really be any random guess, but we allow this variable to be trainable. So as the iterations go on, epsilon gets changed by the neural network to a closer and closer prediction. For our specific epsilon, we have it at 0.05, so ideally at the end of our training, this epsilon will be reflected as 0.05 or a number very close to it. Our PDE function itself encapsulates the Cahn-Hilliard equation, and it's given to the pin via DeepXDE, and this is the basis for the physically informed aspect. Now, down below, equation 1 and equation 2 are our second-order decomposed equations. If you remember in the efficient training strategies, we've said that we decompose the equations to allow for backpropagation to run a little bit smoother, and this is exactly what's being done here. Now that we have all of our functions and constants defined, we can go ahead and dive right into the data loading in pin architecture. First, we load in our initial data. If you remember, this is the output of the forward pin, and that's exactly what we do here. In running the forward pin, we simply just save the output in a text file so we can easily load it up in our inverse. Now, the Cahn-Hilliard physical context is given along with the components of our loss function. You can see here in the data AC that point sizes are given for domain and boundary. We give it the geom time variable, and along with the PDE. The list that you see here is the boundary conditions and initial conditions. Now we can define our network architecture. We lay out our hyperparameters being network size, and DeepXDE actually allows us to create a fully connected neural network. We define this in our PDE using the tanh activation function, and we have a DDE callback, which is for variable value. It just allows us to check in on our epsilon value during the training stage. And we put the network and the data together, and this creates our model in DeepXDE. Now that we have all of our constants and functions defined, we can jump right into the data loading in pin architecture definition. What we do first is we load in our initial condition data, and this is the exact data that is the output of the forward pin. We just save the output to a text file so we can load it in easily. Now we give the Cahn-Hilliard equation to DeepXDE as physical context, and we also do this with the components of our loss function. You can see this at work in the data AC definition. It's a time PDE, which is just a DeepXDE inner working where we give it all of the physical context that we need. And this will be used right below in the network architecture. Right here we define network hyperparameters, and we create a feed-forward neural network, which uses a tanh activation function, and we give this to the model along with our data, and this creates our DeepXDE model that we can train. We will now go over the code used to train our pin. First, we run a training loop for some number of iterations, specifically in the iterations atom constant. From there, we'll train our model 1000 epochs at a time, tracking the value of epsilon as we progress. The model first trains with the atom optimizer, which is a very commonly used optimization algorithm in machine learning. After it trains with the atom optimizer, it then uses the LBFGS optimizer. This specific optimizer allows for some fine-tuning of the model, and it gets at a lower granularity than the atom optimizer does. After training for one loop, or 1000 iterations, we record the training variable epsilon for later visualization. Ideally, at this point, the value of epsilon will have moved some amount in the direction of the true value encoded in the data. We'll continue this training loop until we've iterated for as long as we specified. After training, we create our visualizations. Because this is the inverse problem, there's nothing our model needs to actually predict post-training. We already have our epsilon properly trained. I'd like to thank you all for watching this presentation on using pins for modeling the Cahn-Hilliard equation. I'll have a GitHub repository of this code linked to the video, and I'd also like to give a special thank you to Professor Mahmoud Mamavand and Asfandyar Khan for their help in developing the code and creating this presentation. Feel free to reach out to me via my LinkedIn with any questions you may have, and thank you.